so getting back to this chart, if we increase the temperature, we'll speed up the reaction. We'll speed up the reaction because there's just going to be more molecules colliding. But there are other things, like, for example, if the bonds are really weak, then the activation energy, that hill that has to be climbed, is a lot smaller. And so here it just shows 262. This is for bonds being broken and new bonds being formed. But if the bonds are really weak, the activation energy drops, meaning the fraction of molecules increases and react. Or if the bonds are really strong, then the fraction of molecules decreases. And so the bond strength is going to influence where EA is. Is there a way to change bond strength? Is there a way to make the bond weaker? One way to help weaken the bond is by using a catalyst. You know, catalysts, what they do is they lower the activation energy by making it easier to break the bonds. And so catalysts lower the activation energy. So without a catalyst, we have to break these bonds here. With a catalyst, makes the bond breakage easier, so it doesn't cost as much energy. So if it's easier to go over that little hump, then what's going to result is a lower activation energy. And at the same temperature, we're going to have many more molecules that could potentially react. But if you look at the structure here, the way it breaks is not exactly the same. I mean, if you look, there's two humps here versus one hump. So this is showing what we call a different mechanism for breaking the bond. So this acid catalyzed reaction, or excuse me, a catalyzed reaction here. Here we can see it again. For the catalyzed reaction, the activation energy is lower than for the uncatalyzed reaction. Therefore, the reaction should happen much faster. And so, how does a catalyst lower the activation energy? Well, there are different kinds of catalysts out there. So, let's see. This is kind of a cartoon of a catalyst here, but this is the catalyst, this purple blob here. This is the reaction we want to happen. We want to break apart the glucose from the fructose. This would be glucose. This is sucrose. Sucrose consists of glucose bonded to fructose. And this bond's not so easy to break, but you know what happens with the catalyst is the catalyst pulls on this bond. It puts a tensile stress on the bond, which makes it easier to break. And so when this one locks in here, just by intermolecular forces, it's pulling them apart, and therefore that bond is easier to break. Once the bond's broken, then the catalyst is no longer attracted to this. And the glucose and the fructose break off. We regenerate the catalyst. So the catalyst can be reused over and over again. So it's used and then regenerated, used. So that's a case where the catalyst is weakening the bond. There's cases where catalysts provide alternate pathways. One example of an alternate pathway is something like this. We take this. You know what this is? Here. Not bicarbonate.
Carbonic acid.
Not carbonic acid. This is formic acid or methanoic acid. The formic acid or methanoic acid. It turns out that methanoic or formic acid can decompose. This is called formic acid decomposition. In formic acid decomposition, you know, these bonds can spin around. So let me redraw this like this, make it a little more favorable for reaction. If I look at something like this here, then I take a look at this oxygen. This oxygen is a Lewis and Bronsted base. And we have this hydrogen here. Normally a hydrogen bond to the carbon is not acidic, but this carbon's special. This is not like your typical hydrocarbon. That carbon has two oxygens bonded to it. Having two oxygens bonded to that carbon makes it very electron poor. And so what happens is it makes this hydrogen more acidic than it normally is. And so we have this acid-base reaction that occurs within the molecule. And it's called an intramolecular proton transfer. Intramolecular proton transfer is just an acid-base reaction that happens inside the same molecule. And it has to vibrate. There's going to be a big vibration here. Causes this, like that. So if that gets plucked off there, then we end up forming this. Like this. How does that look? Does that look like a good loose structure? Oh, does everything have an octet? So does it look stable to you or not so stable? Why?
Yeah, the one on the bottom.
You're talking about here?
Yeah.
Oh, because you're saying the charge, right? This is going to come out with what charge?
Plus
And this is going to come out.
minus.
And so is that stable? No, that's not stable. And so this is kind of uphill, you know. Maybe this could happen. But if, in case this happens, what do you think is going to happen? What's going to happen is this carbon's electron rich now. And so these electrons are going to be pulled away by this oxygen. If these electrons get pulled away by this oxygen, then that leaves carbon with less than an octet. If carbon has less than an octet, then these electrons have to come in and bond here. Otherwise, we aren't going to quite have an octet. And so we end up with something like this. We end up with this and this. And so formic acid can decompose into carbon monoxide and water. Is this very favorable? No. It's not very favorable. However, with an acid catalyst, you can make it much more favorable. And so an acid catalyst does something different in this case. You know, because this base had to pluck the proton off the carbon here. But what if we had acid catalyzed? If we had acid catalyzed, the reaction is going to happen a lot easier, because rather than having to pluck this proton off, which is not going to be easy, this is why this is kind of unfavorable. Rather than having to pluck this proton off, what if there's a free proton floating around in acid? You know, acid, we're going to have hydronium ion concentrations greater than the hydroxide ion concentration. So let's say there's a proton here. If there's a free proton here, then is it going to cost much energy to remove that proton? Well, you're removing it from what? Probably just water. Hydronium. And so already, which one's going to cost less energy? This one here. It's going to cost less energy, lowering the activation barrier. Oh, we lower the activation barrier there, but you know, we're going to form this, which is kind of unstable here. Something like this. But this doesn't look so good because this oxygen is positive. If that oxygen is positive, not so happy. And so what it's going to do is it's going to pull the electrons from there. So if it pulls the electrons from there, then carbon's going to be left with less than an octet. So we should try to fix that here. We're going to end up with something like this. You know, there are different ways this can go. We'd have to figure out what that way is. But anyway, we'll form water here, which is stable. But we're going to have this carbon like this. And so the carbon like this, well, it's going to take these electrons from the hydrogen, and it's still not going to have an octet, so we got to have electrons come in through here. And so what ends up happening is we regenerate the H+, and then we end up with carbon monoxide and water. Now that H+, since it's regenerated, can catalyze another formic acid molecule and be reused, cycled over and over. And so overall, this pathway, this what we call mechanism, has lower activation energies than the other mechanism. And so there are different ways that catalysts can work. So this is just two of them. So it's a different, you know, kind of path. Like that. All right, what else affects it, the rate of reaction? Well, 1, temperature; 2, catalyst; 3, concentration. You know, concentration, we can just see here, this. The concentration is just kind of the area under here. So let's say the area contains 1 billion. If we go to 2 billion, then it's going to be much bigger. If it's much bigger, then the fraction of higher energy is going to increase. And so concentration will impact the rate. So the higher the concentration, the faster the rate of reaction. That's kinetics. Kinetics deals with speed of reactions. And so the things that affect the reactions are going to be temperature, catalyst, concentration. We have collision theory to help us understand or visualize it. Okay, part 2 of this chapter, which should be a separate chapter, is the equilibrium. And this is the thermodynamics. You know, where does the balance lie? The balance lies depending on the driving force. Strong driving force, it's going to be all downhill in forward reaction. You know, extremely weak driving force, it's all uphill, very little or no reaction. But if it's somewhere in between, then we're going to have something called dynamic equilibrium, in which, you know, balls can roll both ways, you know, uphill and downhill, downhill and uphill. And then the kinetics part is this. The kinetics part is how fast does it take to establish equilibrium or to complete the reaction. So here it is. Forward reaction occurs and it's going to slow down reverse reaction. Eventually they equal each other. There's no more net change. Where is that equilibrium? Well, that equilibrium we characterize by this. I'm going to jump ahead a little bit and then come back. The ratio or the equilibrium is going to be described by K. We already saw 1K, we saw KW. Kw is that, what we call equilibrium constant. Kw is the water ionization constant, or the water reaction constant. It's Kw. But we have lots of different Ks because we have lots of different reactions. Here's one reaction here. This is a reaction of H2 plus I2 yields HI. Where does that equilibrium lie? And so they did 4 different experiments to find where the equilibrium lies, and this is where it lies. K is just the ratio of products over reactants. And that's products over reactants. Now, the size of K is going to tell you where it lies. For example, what was KW? KW is 10 to the minus 14. 10 to the minus 14 is an extremely small number. It means that this ratio is going to be extremely small. That is, in other words, it's going to be all reactant, very little product. And so this is where, the billion, if I had a billion, then the billion go unreacted, and only about 4 of them actually react. And this is going to give you a very small K. Versus a large K is going to have all products, very little reactant. And so this ratio is going to tell us where the equilibrium lies. Does it favor a reactant, or does it favor a product, or is it somewhere in between? And so large K's favor product, very small K's favor reactant, and K's around 1 favor both. And so if we take a look at this previous reaction and look at the K value, this is the K value they determined from experiment. No matter how they did this reaction, they could use different starting concentrations, do different combinations. They always ended up at the same ratio. So at the end of the reaction, they had a 51.5 ratio. 51.5, 51.5, 51.5. We can use this ratio to figure out the stoichiometry of this, where it's going to end up. Okay, I'm going to back up. Once equilibrium is established, once I hit that ratio, then that's what we call equilibrium. And everything's balanced. And what we're going to talk about next is Le Chatelier's principle. Le Chatelier's principle says, okay, once you hit that equilibrium, like for example KW, in KW it's all water, very little hydronium and hydroxide. But what happens if I add more hydronium to it? What happens if I add more hydronium, I upset the balance. And what Le Chatelier's principle is if you upset the balance, then reaction is going to take place to try to reestablish that ratio, try to reach a new position of equilibrium, And so when an equilibrium is disturbed, the equilibrium will shift in the direction that tries to return the substance disturbed to its original condition. It won't get back to its original condition because you perturbed it in some way, but it'll try to get back as close as possible to that. And so let's say we've reached some kind of equilibrium here between methane, hydrogen sulfide, hydrogen, and carbon disulfide. And so that might be some balance like this. So it's hit the right equilibrium. The products may be more stable, the reactants may be more stable, vice versa. But we can set that equilibrium. So for example, if we increase the H2S, let's say this was the original balance, it favored the product. If we increase the H2S, we're adding reactant or we're adding product?
Yeah.
We're adding reactant. If we add reactant, then is it in the right ratio? No, it's not in the right balance, So what's going to happen is it's going to shift this way to try to reestablish the balance. And so we call that a shift right or forward reaction. And so if we add H2S, then we got to shift it to the right to maintain the same ratio. If we add H2, then we have too much product. We got to shift it to the left to maintain the same ratio. And so to answer these is pretty quick. Increase the H2S has got to shift right. Shifting right means it goes forward. If we add H2, it's got to shift left, which means it goes reverse. And consume some of the added H2. Let's look at this equilibrium. This equilibrium, we're going to look at volume, what volume does. If we change the volume, we might see a shift, we might not see a shift. We got to look, does one side favor bigger volume or smaller volume? If so, then it will shift. If no, then it won't shift. And so how can we tell? We can tell by how much gas we have. Over here, there's 1 mole of gas plus 2 moles of gas. It gives us a total of 3 moles of gas. Over here, we have a mole of solid and 4 moles of gas. And so essentially, the gases take up the biggest volume. And so if we have 4 moles of gas versus 3 moles of gas, which one needs more space? Well, which one needs more space is 4 moles of gas. 4 moles of gas. 4 moles of gas occupies about 100 liters. 3 moles of gas occupies about 75 liters. And so if this is established equilibrium and then we change the volume, then it's going to screw things up. So let's take a look at the question here. If the volume is reduced, which side is favored? The right side or the left side? Volume is reduced. And so this takes about 75 liters, this takes about 100 liters. Which side is favored? The left side. So it's going to shift. It should shift left to take up less space. If the volume is reduced, shift left, reverse. Temperature favors, well, it depends if it's endothermic or exothermic. So this particular reaction is endothermic. So if I add heat, which way should this shift? To the right or to the left? If I add heat, it should shift to the right. But this is like if I add reactant. If I add more reactant, I need to form more product. If I remove heat, then this is removing reactant, it should shift left. So adding or removing heat, we have to look if it's endothermic or exothermic. And so this is going to reverse. The temperature is reduced, so we're removing heat. We remove heat, it shifts to the left. Okay. To achieve this ratio. The ratios vary all over the place. These ratios can be used to do stoichiometry. And let's show you some examples of stoichiometry here. For this reaction, we can figure out the stoichiometry of this by using the K ratio. In this case, it's called KSP, not KW. KSP stands for solubility product. We have KAs for acids, KBs for bases, some Ka calculation. We have KPs for pressures. This is a typical stoichiometry type calculation here. We set up a table like this. This table is called an ICE table. I is initial, C is change, E is equilibrium. So this just describes the stoichiometry in tabular form. That's it. And so I'm going to skip all those calculations. And so we're going to end this here on slide 47. Slide 40, oh no, sorry, not slide 47. We're going to end this here on slide 37. Slide 37 is where we'll stop. Slide 38 through 40, 38 through 60, skip. We, to do this proper justice, we need to spend a lot of time. I mean, just to cover the second half of the week or 2 weeks, we're going to skip it. These are Chem 1B style calculations, and we do a lot of them. About more than half the class involves these types of calculations, so you'll get quite good at them. So we're going to skip it. Instead, I'm going to move to chapter 19. Chapter 19 deals with redox reactions. But we already did some of it. No?
This class needs like therapy sessions. Like right after.
Yeah.
I think we just do that. Yeah.
What's that?
What are you doing for Thanksgiving, Professor Chabelle?
Fun.
Do you make turkey?
It's my favorite.
Yeah, we're gonna have some turkey. Probably some turkey or something.
I'm not allowed in my kitchen for an entire week before Thanksgiving. It's my grandmother should eat.
So she makes good turkey then,
Ever.
right?
Did you ever do a sale? Yeah, it's been set for an entire week. Every cast is there.
Well, we're just gonna hit the first part of this right here, of chapter 19.
I don't want to teach you right now.
You want to just at least have more time to at least.
Wait, so what chapter do you be on the test? All of them.
19.
You have to learn some vocabulary for this chapter. And so let me just introduce it, and then we're going to come back to it again. And the same thing with the earlier stuff. I know I went fast through the other chapters, but we're going to come back and look at some calculations later. I just wanted to get to this because this a lot of people have trouble with the jargon. But one of the biggest applications of redox reactions is batteries. Batteries are also called electrochemical cells. In particular, these are voltaic cells. Voltaic cells generate electricity. And so this is a redox reaction that occurs in a battery here. But for a redox reaction to generate electricity, you have to separate the oxidizer from the reducer. And so what we'll do is we put the oxidizer in one beaker, the right-hand beaker, and we put the reducer in the left beaker here. And so what is the oxidizer? The oxidizer is copper 2. And what do oxidizers want? Electrons. And so copper 2 is going to try to take electrons. It'll try to take electrons from water. Will it be successful? No. It'll try to take electrons from glass. Will it be successful? No. It's going to try to take electrons from this piece of metal is called the electrode, and this electrode is made out of copper. Will copper 2 take electrons from copper metal? It could, but if it did, what's going to form? If copper 2 took electrons from copper metal, it would form copper metal and copper 2. And so there'd be no change. And so copper 2 is not going to oxidize copper metal. And so there's nothing it can take electrons from here. But we can take advantage of a property of metals. One property of metals is metals are thought of as a sea of electrons. If it's a sea of electrons, if copper 2 is trying to pull the electrons from here, do you know what? It's going to be felt all the way up here. Because something's pulling on this end of the pull, you know, you're going to feel it up here at the opposite end because the electrons are all in this vast pool or vast sea. In other words, there's a train of electrons. But, you know, even though there's a train of electrons here, copper 2 is not going to be successful in taking any of the electrons. And you know what this is? This is going to be a piece of copper wire. Unsuccessful. And then up here, this is going to be a piece of tungsten wire. Unsuccessful. Copper wire, not successful. And then finally over here, this copper wire is attached to zinc. Is copper 2 capable of taking electrons from zinc? It turns out it is. Actually, copper 2 can oxidize zinc because copper 2 is a stronger oxidizer than Zn2+. Zinc is a stronger reducer than copper. This is a single replacement reaction. And so what happens is this. We have indirect oxidation. And so the copper 2 is pulling on electrons, the electron chain is being pulled, and finally, copper 2 is going to be successful. It's going to take electrons from zinc. When copper takes electrons from zinc, zinc becomes oxidized. Zinc goes from Zn to Zn2+. In the process, it loses 2 electrons. Those 2 electrons get fed out. We call this an electrode 2. It gets fed out this electrode to the wire. It goes through the wire, through the light bulb, lights up the light bulb, continues through this way, and gets pulled to copper 2. When the copper 2 takes the electrons, it's going to deposit copper metal on here. And so the copper 2 takes the electrons to form copper metal. That's called reduction. So copper 2 is reduced to copper metal. And so the jargon is confusing because copper 2 is the oxidizer. The oxidizer gets reduced. Zinc is the reducer. Zinc, the reducer, gets oxidized. And so we have to keep that in mind. And so one way to keep that in mind is this, oil rig. Oil stands for oxidation is loss. Oxidation is loss with electrons. And rig stands for reduction is gain. Reduction is gain of electrons. And so copper 2 is gaining, zinc is losing. Zinc loses, therefore it's oxidized. Copper 2 gains, therefore it's reduced. All right, now to make a battery, there are other components here. You see some other stuff in here. Well, that other stuff is critical because what happens is this. This is probably copper 2 nitrate, and so there are nitrate ions in here. And if all the copper 2s are disappearing, then the nitrates are going to get very lonely, right? Because there's no cations, only anions. Is that going to be very stable just to have anions? No. That's going to be terribly unstable. In fact, it's going to be so unstable, it's going to stop the reaction. And so what we have to do is we have to replenish the cations. Otherwise, the anions are going to be very unstable. And we don't have to replenish it with copper 2. We can replenish it with anything. And in this case, we're going to replenish it with potassium ions. This is called a potassium sulfate salt bridge, but we could use sodium ions. We could use any cation. They're using potassium ions here. So for every copper 2 that we lose in this reaction, 2 potassium ions come in here to pair up with the nitrates. We aren't going to get a precipitate, but we'll just maintain electrical neutrality. And the same thing over here. We're generating Zn2+, but we're not generating any anions. And so we just are generating cations. If we generate cations, we can't just have a beaker full of cations. We need some anions there too, otherwise the static electricity buildup is way too high and it stops. And so what happens for every Zn2+ that gets formed, we have to have a sulfate go here. And so what we do is we add sulfates here, the anions. We add potassium ions here, the cations. And so the cations go to this electrode. If the cations go to this electrode, we call it the cathode. The anions go to this electrode, we call it the anode. An for anion, cat for cation. The cathode is positive because the cathode's sucking electrons, electrons being negative. So the cathode's sucking electrons into the battery because of the oxidizer. The oxidizer wants electrons. And the anode's negative because the anode's generating electrons. The electrons are being generated at the negative and going to the positive. And so we have our battery here. This is going to generate electricity.
That's a voltaic cell. We're almost done for today.
Good.
And then we have the salt bridge is that.
And the electrode.
The electrodes, the cathode and the anode. So we're going to skip this slide here. This is the same reaction.
The copper 2s are taking the electrons from the zinc, but this is direct reaction. And so the copper 2s are attacking the zinc directly. If the copper 2s attack the zinc directly, the electrons are transferred directly. And this is not going to generate any electricity. We have to keep the copper 2s separate from the zinc in order to generate electricity. So this is a reaction progress. The copper 2 is becoming more dilute, and then the copper metal is becoming more This is another direct redox reaction. This is silver ions oxidizing copper here. This is direct here. So silver ions will take electrons directly and deposit silver metal and generate copper 2 ions in the process. Copper 2 ions. You can see that as the blue color comes up and the silver crystals grow. All right. Okay, we'll stop here. Alright. So, anyway, have a nice Thanksgiving.
You do.
Oh, it's a quick color reacted. Why like it's breaking in my like fingernails? Yeah, like a pencil. Throwing pieces. I recommend or just want to do.
You're 21.
You do? Oh, that?
Timmy's mom gonna do to me if I don't play sports.
Or she's gonna call the manager.
Have a good Thanksgiving. Hey, thanks. You too.